Alright, so this time we do a little bit, I take it up a notch or two. Something that maybe it's not quite as obvious as the other ones we've been doing. Nevertheless, the steps are always the same, man. We're going to try to look at it. We're going to try to see what it smells like. We're going to verify by checking this limit. We're going to check our conditions are good. Boom. We're going to declare this one similar to the one we think it smells like, and life will be good. How's that sound? Good. I know it sounds good to you. Alright, let's do it. Let's do it. Talk is cheap. Alright. Man, I only get this many colors? What the hell? I wish I had more colors, because I'm already tired of these ones. Alright, I'm gonna go with yellow. What a surprise. Alright, whatever, don't judge. Alright, so here, what does it smell like? This should take you back to first semester calculus course, and back a long time ago. Let's just do a little thinking bubble. Think. From a long time ago, you probably encountered a very famous limit as x runs to 0 for sine of x all over x. And you probably did it using the squeeze theorem, L'Hopital, a bunch of different ways. You know that that limit is 1. You've done it a million times, right? So today we get to see the same sort of limit dressed in a different way. Think about it. You have the limit as n goes towards infinity. What would happen if you have sine of 1 over n squared all over 1 over n squared? In this case, your n's are running towards infinity, so this is running towards 0. And it's exactly identical to the angle, which is also going to 0, of course. Gives you the exact same scenario as the famous one that you did before. So clearly this limit would be equal to 1. Okay, it would be really funny if this limit was 1 and this limit was 2. Or you could use L'Hopital here if you're not convinced. The same as you could have done L'Hopital over there. Whatever. This is super famous. But think about what the implications of that. This tells you something of the same sort of as this thing. This tells you that if the limit of a sequence A over or Bn, an over a Bn is equal to k. Remember what we said here? This meant that an was approximately equal to the k times the bn, right? That's exactly what it means when the quotient is equal to k. Well, the same thing here. If this quotient is equal to 1, that means that sine of 1 over n squared must be approximately 1 times 1 over n squared for large n's. This is fancy little sniffing, fancy smelling, huh? So that leads me to believe that this one smells like 1 over n squared. Boom. Now I just need to verify. Of course, the verification would be this step right here. I take the sequence I have, I take the one that I think it smells like, I slap a limit on it, boom. So of course this is again the first semester problem, or you can use L'Hopital. If I try the plug-in method here, plugging it in, I get 0 over 0. So I try L'Hopital just for fun, in case you forgot your first semester. This would be cosine of 1 over n squared times 1 over n squared prime. This would be, and then you do the same thing on the bottom, the derivative of the bottom. Whatever this is going to go away, so then I could try my plug-in method again. Of course, all these should have limits as n goes towards infinity, so you get cosine of 0, which is equal to 1. I told you. See why they pay me? Winner, chicken dinner. Alright, what does that do? That tells you that they behave roughly the same. Oh, wait, we gotta check the condition here. Of course, all your 1 over n's are positive, so boom, done. Can't believe I get paid to do this. Insane amounts of money. This is robbery. That's why the government is doing so many furloughs. They're running out of money because they pay people like me for doing kind of stuff like this. Crazy. Alright. Again, I got off on a tangent. Alright, so verifying these two steps tells you that this one behaves roughly the same as that one. So let's go on to the next step. The next step would be then just make the statement here. Then these two behave roughly the same. And now what? Well, this one is super easy. You could do it by integral test. This converges, so therefore the other one converges, and you're done. Or you could just say by recognizing this is a p-series where that number right there is bigger than 1. And you're done. See? See how easy that is? Alright. Sorry it ended so abruptly, but that's how it goes sometimes. We'll see you guys here next time for another excellent example. Peace.